What's up, YouTube? Optical Info back with another weekly video. Back to the roots here. In this one, we're coming from the car. It'll be a little bit different, but I think we can get it done. Got a little early to work this morning. Let me show you this. Let me show you this beautiful skyline. Ooh, quick teaser. Back to optics. All right. Let's see if I can get some of that in the background. So, where are we? Number 21. What's it say here? A child wearing a full cyclopegic refraction has a 15 prism diopter esophoria at 0.5 meters. With a -2 lens over her glasses, the esophoria increases to 15 prism diopters. What is the AC over A ratio? Well, if you've never heard of that AC over A, that just means accommodative convergence to accommodation ratio. Okay, so the convergence over the accommodation. So this one's actually pretty simple. We know that the convergence, which is measured in prism diopters, changes by 10. Okay, so that's our AC in the numerator. And then the accommodation, she's having to accommodate through that -2 there. So it's going to be, that's going to be our denominator. So 10 over 2 is our answer, which reduces to 5 over 1. Okay, so that was pretty simple. Number 22, moving right along. How much, this is supposed to say prism, how much prism is induced if a -6 lens is held in front of the left eye such that the optical center of the lens is 5 millimeters lateral to the visual axis? Okay, so this is just Prentice's Rule, which is also simple. It's just the prism diopters is equal to the height in centimeters times the power of the lens. So in this case, we've got, I'll write it up here. We're doing 5 millimeters lateral. Usually we're talking about inferior with like a bifocal or something, but for this it doesn't matter. It's the same formula, which I'll write here. Sorry for being awkward. So I'll write it big on up here. Prism diopters is equal to the height in centimeters times the power. I don't know what the actual letters are supposed to be. So this would be equal to -6 is the P there. And the height is 5 millimeters. It's supposed to be in centimeters. Don't let that trick you. So that's gonna move the decimal place over 1, 0.5. 6 times 0.5 is 3. So that's our answer. 3 prism diopters. Is that the question? How much prism is induced? Yeah, 3 prism diopters. Okay, easy enough. All right, I had to move back to the top-down view. It was getting a little awkward there. Okay, so number 23. A patient wears the following prescription, blah, blah, blah. His bifocal segment is located 10 millimeters inferior to the optical center of his glasses. How much relative prism is induced when he's looking through the top of the bifocal, okay? So again, this is our Prentice's Rule problem with a little twist. All we have to do is figure out the vertical powers and compare the two between the eyes. And we don't care about this add because this is relative prism, the right eye relative to the left, how much prism is induced between the two. So, this is just a little trick here. We can just ignore the +3 and we'll just figure out the vertical power of this with this prescription, okay? So let's draw first I'm gonna label this as a power cross because it is not axis cross. And so here's our power cross here. Let's draw it out. And our prescription, we'll start with the right eye. We've got -1. Where does it go? I never know. So I always put it in a little corner like that. But the +3 is at an axis 180, which means the power is going to be acting vertically here. So our +3 is going to be right here. How is it actually +3? No, it's -1 +3, which is what? +2. And then we know our -1 is going to be over here, obviously. Okay, so this is -1 plus 3 gets you to +2 in the vertical meridian here. Okay, now what about the other eye? Well, let's find out. -3, where does it go? I never know. I always put it here. Plus 150 at the axis 90. So that means its power is acting horizontally here. So -3 plus 150 gives you what? -150. And now we know that this goes over here. Okay, so now what do we do? Well, they're talking about in the question, we're talking about when he's looking where? Through the top of the bifocal. That's a fancy way of saying, and we know the top of the bifocal is 10 millimeters inferior to the optical center, which is the at the cross here. So he's looking down. He's not looking to the left or to the right. So we don't care about what's in the horizontal power. Okay, we just care about the vertical power, and it helps me to draw these vertical bars out as a plus or a minus lens. So I know that a minus lens is going to be like this, and a power lens or a plus lens is going to be like this. And if you want, you can draw this even more like just two prisms, apex to apex, or in this case base to base. Now that I'm making a huge mess, my paper will move along. So what's the relative prism induced here? Well, we just do our Prentice rule now. The prism induced, prism diopters times H in centimeters times the power. I'll write it over here as well, H times P. And for this one, that's going to equal what? Our power is 2. Our prism is our height is 10 millimeters, which is 0.1. I'm sorry, 1 times 2, which equals 2 prism diopters over here. 2 prism diopters. And what is it? We're looking now. We're having this guy look down here. So this is base up, and over here our height again is 1, and our power is -3. So it equals -3 prism diopters, or it's just going to be 3 prism diopters in the opposite direction, which is base down. Now, so the relative difference here, one's base up, one's base down, is going to be a total of 5, So, well, actually, never mind. I think you can understand that, because in the problem they list all of the prism as being over one eye, so you just have to sort of get the cumulative instead of being split between the two eyes. You just get the cumulative difference of prism, which is going to be 5 prism diopters. And if they're talking about just over the right eye, we've got a base up prism over the right eye, so it's going to be E. 24. What is the equivalent prescription of the cross cylinders +1 times 45 axis 45 combined with a -3 axis 135? No problemo. Okay, so this is a power cross again. Actually, this is our typical power cross drawn at 180 and 90, but it's the same thing as if we twist it. Now this is 45 and this is 135. Okay, but the principles don't change, so don't get thrown by that. But let me draw it more appropriately for you. So the first one is +1 times 45 +1 axis 45. This is our axis at 45, so that means but this is going to be a power cross, so we're not going to do that. Axis 45 will get us power at 135, so this is going to be +1 here. And then what's our other one? -3 axis 135, so that's going to be -3 at a power of 45. Now note that we don't, this was not a sphere with an additional cylinder power on top of it. You know, this is not a spherocylindrical lens where you have a foundation of a certain power sphere that you're then etching in a cylinder power. These are just two separate cylinders. So it correlates directly to the power cross regarding the power that you're putting at these different meridians, okay? So +1 over here, -3 over here. What's the question? What's the equivalent? Oh, so it wants us to make a spherocylindrical lens. I'm an ophthalmologist, ophthalmology resident, so I like to use plus cylinder. So we start with the most minus as my foundational sphere. So -3 plus, we're going to etch in a certain amount of power to get to +1 at acting at 135. So the way that you do that is you'd have to add 4 to get to +1. So +4 axis is going to be opposite, so it's going to be right here. So -3 + 4 axis 45. All right, number 25. The spectacle correction of a patient is okay, blah 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 blah. Before we get lost in the weeds reading this long problem with a bunch of different numbers, I first want to back up and explain things from a 1,000-foot view, okay? So in this problem, number 25, essentially what it's asking is, well, you've got this patient who's wearing glasses that wants to go to a hard contact lens, an RGP lens, or gas permeable lens, okay? And so there's two main things that this is testing you on. One is, of course, we're going from spectacles to contacts, so you have to be able to change the prescription for a zero vertex. A vertex distance of 0, essentially. That's easy. That's the lens effectivity formula, which I'll show you, or you can draw it out the way I did in the previous video. But I'm going to introduce it. I'm going to do the lens effectivity formula for this one because it's just sort of a long problem, and that formula makes it a lot quicker. Okay. Anyways, that's number 1. That's easy. We already know that. The other thing that you have to understand about this problem is what's going on with the fit. There's a couple things going on with when you're fitting a hard contact lens, and this is all theoretical for me. I've never done this before, so if you notice something incorrect, please let me know in the comments below. But this is my understanding. First, when you take a hard contact lens and you slap it on someone's eye, even let's say the hard contact itself is a plano lens, okay? A plano hard contact lens, I slap it on your eye. Depending on how it fits, it's going to create a tear lens. And the tear lens could be a plus lens or it could be a minus lens. I'll try to show you an actual picture. Let me demonstrate with my fancy high dollar props here, okay? So this is a paper plate that I folded into a cornea, okay? And what I mean by that is it's a spherocylindrical surface. It's got a flat K and a steep K, okay? Just like a cornea, it's got some astigmatism. One side's steeper than the other, okay? Now, we'll get to that in a second. First, what I want to demonstrate is the tear lens. If we take a contact lens and we plop it on the cornea and we find that it's a bit steep, then it's going to create a little additional plus tear lens there, and you can sort of see that. And that's going to have to be neutralized with some minus in the contact lens power, and that's where that steep add minus comes from. Vice versa, if we put a contact lens on the eye and we find that it's fitting a little bit flat to the cornea, then it's going to make a minus tear lens, and you can sort of see that here. And so we'd have to neutralize that with some additional plus power in the actual contact lens. And so that's the SAM FAP. Flat to the cornea, it's going to create a minus tear lens. You're going to have to add plus to neutralize it, okay? Well, that's great. SAM FAP's great. But the truth is, ain't nobody got time for that, okay? We're not going to be putting trial lenses on, see how they're fitting, see how much plus or minus tear lens is being induced and correcting for it. Nobody got time for that. Isn't there a rule of thumb that we can apply that'll work for most people and be relatively accurate? Yeah, there is. And different people have different rule of thumbs, different rules. Dr. David, so what is it? Let me get to the gist of it. The gist of it is you take the flat K, not the steep K, you take the flat K and you add a little bit of steepness to that. You're not matching it perfectly, because then no tears would get in there. That would be uncomfortable. So you take the flat K and add a little bit of steepness to it, and then, without even doing any trial over refraction, you're gonna build in a little bit of extra minus. Okay, you're making it steeper, add minus. That's SAM. And how much minus do you put into it? That varies depending on who you are. Dr. David Hunter does a half diopter steeper. Dr. Sickelman, who made these problems, takes the difference between the two. Doesn't split right down the middle, but he takes the difference, multiplies it by 1/3, and adds that to the flat K. The gist of it is you just take the flat K, add a little bit of steepness, and then build in some extra minus into your lens to compensate for that plus to your lens that's being created. Why do you use this? Why does everyone sort of try to match the flat K as opposed to the steep K? Well, look, imagine if we tried to fit a contact lens on this. Here's our contact lens. That's relatively close in steepness, okay? We want to match it so that it fits relatively stable and comfortable, okay? So here's our contact lens. Let's put it on our cornea. Uh-oh. It hits the flat K. It can't, it looks like these match up nicely, but you forget that you have a flat K here that it's gonna bump into, and it's not gonna stay on this. It's terribly unstable. You can't match the steepness because the flat K gets in the way. Now, let's match the flat K. This is the opposite. This is what everybody does. They make it a little bit steeper than the flat K, and then you get a little bit more stability. That stayed on for a little bit longer, okay? Let's see if I can. See, I can even balance it there. Okay, so you get the gist of it. You can't match the steep K because the flat K gets in the way. Okay, at least that's how I think about it. So before we get back to the problem, what we're going to do is a few steps, and we're going to just use this flat K. We're going to use the power along this meridian as the power that we're going to convert from the spectacles to the contact lens, and we're going to use this base curve for the fitting for the base curve of the contact lens. I don't think this problem is asking for it, but that's what we would use this curve, and then the contact lens would fit on top of that. The cornea is sort of falling off in front and behind, and that astigmatism is just going to be erased, so you can just completely ignore it. And we're going to use the sphere along this meridian. Okay, so let's look at that in the problem. All right, 25, ignore all this other writing here, sorry about that. 25, the spectacle correction is this. This is the vertex distance, 10 millimeters, and there's K readings of 45 at 45 and 42 at 135. So what does the lens power need to be for the RGP, using the typical rule of thumb, where you have 1/3 of the K difference added to the flat K. Remember that this is just what Dr. Sickelman likes to do. Different people do different things. And so how are we going to approach this problem? Well, we know it's from the concept stuff, but this is what we're going to memorize, okay? These are the steps to taking an RGP, glasses, and going to an RGP. First, you determine the spherical power, which is that power, the power of along that flatter meridian. And the way you'd figure that out is you just convert it to negative cylinder, and then you ignore the cylinder, or minus cylinder. Number two is you're going to take that spherical power and convert it from the glasses to a zero vertex contact lens of prescription. And we'll do that with our handy dandy lens effectivity formula, or you can draw it out, whatever you prefer. And then number three is we're going to subtract the tear lens that is induced. So determine the spherical power, convert to zero vertex, and then subtract out that tear lens that's induced. Okay, so let's apply these three steps. So First, we'll determine our spherical power by putting the prescription in minus cylinder if it's not already, and it is not. This is a plus. So the way we do that is, we add it to the sphere. Plus -9 plus 3 will give us -6. And then we switch the sign for the sill, -3, and we also switch the axis 90 degrees times 135. Now remember, this is an RGP, so this cylinder we don't care about. So we're just going to ignore that. All we care about is the spherical power along that flatter meridian here. So this is what we're going to use. -6 is our spherical power. Now what do? Convert to 0 vertex distance using our formula here. The glasses prescription over 1 minus the glass prescription times the vertex distance in meters. And the power and the sign matters here for the glasses. So let's draw this out. I'll write it again. Contact lens equals the glasses over 1 minus the glasses times the vertex distance, and that's going to equal -6 over 1 minus a small number, the -6 times the vertex distance in meters. So instead of so what is it, 10 millimeters, that would be 1 centimeter, and then 0.01 meters times 0.01 meters. What does all this equal? I don't know. Switch over to the calculator. It comes out to -5.66. Okay, and these, so don't lose track of your signs here. So this is our RGP power. Okay, and now if we just slap this on, remember we made it a little bit steeper than the cornea is, so it's going to create some plus tear lens. So we have to subtract out that tear lens. And how much do we take off of this? Well, if you want, you can just subtract off a half diopter, so just -0.5. Or if Dr. Sycamore, the way he likes to do it is he takes the difference between the two Ks, which is one's 45, the other's 42. The difference is 3, and he multiplies it by a third. So 3 times 1/3 gives you 1, and he adds that to the flat K. So 1 to the flat K, so he just subtracts out 1. So -5.66 minus 1 equals -6.66, and that's it. So it's a long problem. Let me know if you have any questions. It's actually not a long problem. Just do the 3 steps, and it's quick. Just memorize them, just bang them out, and then you'll be done. If you have any questions about anything, just leave them in the comments below. Hope you enjoyed it. Hey, from now on, you stuck it out. You got 4 videos done. That's all you really need to know. Or that's as much as I want to know. All you got to do now is just watch those videos. You don't have to keep doing the problems over and over again. You've walked through them yourself once before. Just play them in the car as you're driving to work or driving home, and it'll be reinforced because you've done them in the past. And so you can remember it come test day. Just enjoying this scenery here. Anyhow, it's been real. Catch you in the next one. Peace.